Okay, hey gang. Something a bit different today. I'm in the same boat as the people of Queensland on this one. I haven't done a whole lot of physics revision, so why don't we do it together? That's my suggestion. And you're more than welcome to come along for the ride. So with me right now, I have the 2020 past paper. I have the 2021 past paper. I have 2022, and I have the 2020 sample. And as I go, right, I think some of these are going to have to be a bit open book. You know, I haven't put the work in thus far. That's what we're doing now. That's what we're doing the Savo. So look, I'll be real with you. At points, I am going to have to open that textbook and consult, and we'll be transparent about that. Now, if you can see in the top left, I've got that timer there. I'm going to try and explain what I'm doing as I'm going, but we're going to be mindful of the time. That's 10 minutes perusal plus 90 minutes per paper. We'll see how that goes. I'm hoping that we'll be able to get them done quicker, but yeah, we'll see. All right. I have the chat up. Okay, so if I'm struggling with a question and you know the answer, just tell me. Just tell me. We're going to start, I think we'll go in reverse order. So I'm going to start with 2022 because game plan, they're not going to ask the questions that they asked last year again this year. That would be a fool's thought pattern. Perhaps QCEE will get lazy and they'll ask something from the 2020 sample again. So we're going to do that one last. Let's get into it. Paper 1, 2022. So I've got the formula sheet. And we've got multi-choice question book, paper 1. All right. So I'm going to start my 10 minutes perusal time. All right, multis. Looks like we got a bit of, what is that, electromotive force. Okay. All right, let's break the rules a bit here. We're going to start the multis in perusal time. Question 1, electromotive force is, looks like the production of voltage across an electrical conductor due to its dynamic interaction with the magnetic field. So I'm thinking A. This is potential difference, it's not B. That's just electrostatic force, it's not C. And it's not one of the 4 fundamental forces, so we're going to go A. A photon is described as a quantum of all forms of electromagnetic energy. So it's not A, because we know a photon is particle model of light. We're not talking about a continuous wave. And it's not a particle that can only propagate in a medium because, well, we measure the speed of light in a vacuum, which is the opposite of a medium. That's no medium. It's not a particle that mediates the force between protons. It mediates the electromagnetic force. But yeah, I'm not thinking that's the most correct definition. So C, a quantum of all forms of electromagnetic energy. Could be a quantum of X-ray energy, light energy, whatever. So we're going to go C. Which free body diagram best represents an object being pulled at a constant speed up an inclined plane? So immediately I'm thinking constant speed. So we need zero net force, constant speed. And if I add all the vectors together, just by looking at this, then I want the vector sum to be zero. So we'll start with the vertical direction, let's say. So I'm going to split gravity up into perpendicular and parallel components. See that? So the vertical component of gravity is definitely balancing out that normal force. But it looks like if I add this horizontal component of gravity onto the horizontal force of friction, then these are not balanced. So it can't be this guy because we've got a net force going this way, if you can see that, if we add those together. So we want a horizontal force of friction that is less than this force because gravity is going to oppose the motion that way. So if I split this one up, oh, this looks promising. So let's add that arrow onto there. Yeah, and that looks about balanced, doesn't it? So I've added the horizontal component of gravity onto the force of friction to get the net horizontal force. And it's looking like the vertical force is balanced, the horizontal force is balanced, so I'm going to say A. Okay, we might need the calculator for this one. An object orbiting Earth has an orbital period, T, 5.6 by 10 to the 3 seconds. What is the object's orbital radius? I'm thinking this is Kepler's law. So it's going to be that formula there. T squared over R cubed equals 4 pi squared on GM. Okay, so we know T, and we are looking for R cubed. So let's just rearrange this formula real quick to get R cubed in terms of all of this stuff. So T squared equals all of that times R cubed, yeah? So R cubed is going to be T squared divided by all of that, which is the same as multiplying it by the inverse. R cubed is going to be T squared GM on 4 pi squared. Because we've divided both sides by this fraction, or multiplied it by the opposite, the reciprocal of the fraction, if you will. So then R is going to be the cube root of this 4 pi squared. Now I like to rearrange before I put the numbers in there. And I don't really like to use solve_n because, well, sometimes I like to use it. I like to use it to check my answers, but sometimes I put it in solve_n and it just tells me there's no solution, especially when I've got lots of scientific numbers in there. So yeah, whatever. Do what you want to do. So I'll put this in my calculator and we'll sub in the numbers that they've given us. It's the cube root of T squared. They've given us T in seconds. We've got to be careful about the units. 5.6 by 10 to the 3 squared times G, big G, that's a constant, gravitational, constant or whatever. It should be in here somewhere, yeah. So you can see down there, big G, 6.67 by 10 to the negative 11. Big M, so that's the mass of Earth, the mass of the thing we're orbiting. We've got that there, down the bottom. Okay. ME equals 5.97 by 10 to the 24. Over 4 pi squared. So that's given me 606,802,097. So that's 1, 2, 3, 4, 5, 6, 6.8 by 10 to the 6 meters. Let's put that there. Tau particles. Okay. Been a while since I've done standard model, but we know electrons are leptons. Because electron neutrino, leptons have a neutrino, electron neutrino, so electrons a lepton. So that means tau, we know tau has a neutrino, tau neutrino, that means tau is also a lepton. It's definitely not a baryon, because it's not made of quarks. That's just a rote learning thing. Yeah. If you want me to do if you want me to get the whiteboard out and do standard model, happy to, but yeah, just memorize it. After coherent light has passed through a double slit, the observation of an interference pattern on a screen is explained by the R. This one's interesting. Yeah, so this is Young's double slit experiment. He put 2 slits in his little screen, and he shined a coherent source of light through there, like through a pinhole in his window or whatever. And he got this diffraction pattern on his, he had this photosensitive thing. So when light shines on it, it kind of stains this material that he's got. And he got this diffraction pattern with all these different bands of light. So he had 2 slits, right? He got a slit here and a slit here. And instead of the light just shining on there and shining on there, he got this weird pattern. Some of the light was there, some of the light was there, some of the light was there. And he explained that by going, oh, well, if these are little wave fronts, say we dropped a rock in a pond and we've got these little wave fronts, then when the waves hit each other, they're going to constructively and destructively interfere, if you remember that from year 11. So basically, if you have 2 waves and you put them on top of each other, the amplitude of the 2 waves just adds together. So the intensity of the light gets bigger. And this diffraction pattern then is explained by the wave nature of light, because it's caused by these wave fronts interfering as waves do. Diffraction, interference, diffraction. Oh, perusal time's up. let's. Okay. Yeah, you can just think of it diffraction is something waves do. Interference, constructive, destructive interference, that's something waves do. So it's wave nature of light. Which change would produce the greatest increase in magnetic field strength inside a current carrying solenoid? Okay, so this is coming to the formula B equals mu naught Ni. That is magnetic field strength inside a solenoid, that one. Let's write that down. So it's affected by, that's just a constant, that's our magnetic permeability constant or whatever. That's number of coils in the wire, or number of coils per meter, sorry. So turns per meter. So if I have a, 1 meter solenoid, I have 1, 2, 3, 4, 5 turns, well, it's just 5 divided by 1, 5 turns per meter, right? That's N. And I is going to be the current in the wire. So decreasing the thickness of the wire, we're not really thinking about that. That's not in the formula that we've been given. Increasing the length of the solenoid. Now, if we think about that, if we increase the length, but we don't change the number of turns, then the turns per meter is going to go down. So that's not going to increase the magnetic field strength. That's going to decrease it. Adding more turns of wire may increase it, because if we keep the length the same, but increase the number of turns, then N's going to go up. Using an alternating current instead of a direct current will not necessarily increase the field strength. So C, because that's the only one that clearly increases N, or increases the value of B in that formula. Okay, determine the wavelength of an electromagnetic wave with energy 2.4 by 10 to the negative 3 joules. I'm just going to go this formula. So wavelength equals hc on lambda. Oh, wait. What? The wavelength. Okay. Nah, I'm gonna have to think about this one. So we know energy of a photon, or energy of, an electromagnetic wave, HF, and F is going to be equal to C on lambda, because we know frequency, or like time, you can think of that, is speed on distance. So that's going to be, oh yeah, okay, so E equals hc on lambda. That means lambda equals hc on E. Let's put that in our calculator. I'll just clean that calculator screen in a sec. Okay, Planck's constant, what is that? Kyle's World says, yo, check Q1, boss man. Let's just go back and check Q1 real quick. True. He's got a point. This sounds like electromagnetic induction. So electromagnetic induction is the process by which voltage is produced across an electric conductor due to its dynamic interaction with the magnetic field. So that would be the definition of electromagnetic induction. And I said it wasn't B because I said B is potential difference. But electromotive force is potential difference. They're the same thing. Thanks, Kyle. Thanks, boss. So it's B, not A. A is the definition of electromagnetic induction. Anyway, back to this. Wavelength equals hc on E. So what's H? (6.626 by 10 to the negative 34 times the speed of light. I should know that. 3 by 10 to the 8 on energy. 2.4 by 10 to the negative 23 joules. They've given me that. 8.2825 by 10 to the negative 3. That's close to this one. Let's see. Okay, which diagram would result in the furthest horizontal distance traveled? Well, we want the greatest horizontal component of velocity, because if you remember it will be in our linear motion formula. Where are they? So the horizontal distance traveled, or the range, Sx, is uxt. So the greater the initial horizontal velocity, the greater the distance traveled. Now my only thing there is the time will vary. Because if we have a higher launch angle, say it's going to be in the air for longer, so t is going to be bigger. So we might also need to consider just finding t. Yeah. Well, we've got this one. I don't really like this one. To determine the vertical displacement from the initial y velocity and the time. So we can find the time of flight using that. Let's take a gamble and say, okay, if this one's got a big launch angle, it's probably going to be in the air for a fair while. But it also looks like it has a reasonable amount of horizontal velocity, v equals 11. So that would be 11 cos 45. So I'm going to say, this one looks like it might have a good balance of time of flight and time of flight and initial horizontal velocity. So initial horizontal velocity 11 cos 45, 5.77, or 5.78 meters per second. And time of flight, so I'm going to sub in like 0. Let's say sy equals 0 is the ground level. We want to find when it reaches the ground again. So 0 equals 1/2 gt squared plus, and initial vertical velocity is going to be 11 sine 45. Oh, I need to change my calculator to radians, to degrees, sorry, from radians. Let's just do that again. Yeah, so that's 7.78, not 5.78. So what did I say about this one? This is a case where I'm going to use solven. So calc solven 0 equals 1/2 g 9.8 t squared, so x squared, plus initial vertical velocity 11 sine 45 times x t. So let's solve for t. Oh, sorry, g should be negative because we're going down. Yep. So time would be 1.58. We're not taking 0. That's when it's on the ground. 1.59 seconds. So 1.59 by 7.78. That's our range. 12.37 meters horizontally it's going to travel. Now we can repeat this real quick for the rest of them. That process. So we're going to go 11 cos 20 times, oh well, we'll have to find time of flight first. So let's just change our launch angle 20 and magnitude of initial velocity. So the time for that one is 0.83, and that's, so it's going to be 0.83 times 12 cos 20, 9.35, which is less. So lower. Now we can just immediately rule this one out because same launch angle but magnitude of velocity is less, and we can rule that one out too because same launch angle, magnitude of velocity is less. So that's going to produce less range than, sorry, this is going to produce less range than that. That's going to produce less range than this. So we're going to say B. Electric field strength refers to the intensity of an electric field at a particular location. Yes. Change in electric potential energy between two defined points. No, that's potential difference. That's current by the sounds. And what's that? Physical property of an object experiencing a force or not? Yeah, not really. Not really. That's just electric strength of an electric field, intensity of the field at a location. Sounds about right. Okay, the maximum kinetic energy of an electron ejected from a metallic surface can be increased by using a positively ionized metal. I don't think so. With a large... Okay, I'll just write down the formula here. So we know the kinetic energy is hf minus w. So that's the energy of the photon you eject, and that's the work function of the metal. So that's going to decrease it, because if that's bigger, that's going to decrease the kinetic energy. If I increase the intensity of the incident light, that's not going to do anything. There's no term for intensity in here. There's frequency. Frequency of the incident light. Sorry, yeah. That's kinetic energy of ejected photon. This is frequency of the light that you shine on the metal. Intensity isn't going to do anything. But if I decrease the wavelength, then I increase the frequency, right? So this is increasing, therefore that's increasing. D. An object experiencing uniform circular motion in a horizontal plane travels at an average speed of 8 meters per second. Okay, calculate the radius of the object's path. So circular motion. God, it's been a while. Let's have a look at our formulas. It looks like it's going to be something like this, because they've given us how long it takes to complete a full rotation. We call that the period of the motion, t. And we know v. They've given us the average speed. So this one, we're looking for the radius. V equals 2 pi r on t. Let's rearrange. Vt equals 2 pi r. So r is Vt on 2 pi. Let's put all this stuff in our calculator. They've given us V 8 times t, 0.3 on 2 pi. Beauty, 0.38 meters, which would be 3.8 times 10 to the negative 1. Rectangular coil of 3,000 turns and dimension 0.1 by 0.2 meters is rotated in a uniform magnetic field of 2 millitesla. Calculate the minimum number of revolutions per second required to produce an average EMF of 6 volts. Jesus. Okay, let's think about this. It's like a solenoid, right? 3,000 turns. So 0.1 by 0.2, I'm assuming that means... You know what? Let's simplify this a bit. Let's just say it's a rectangular coil. Okay, let's just say it's a square to simplify things. And, it's 0.1 by 0.2. So there's 3,000 turns of wire in this rectangle, 3,000. And let's say 0.1 meters that way, 0.2 meters that way. It's being rotated in a uniform magnetic field of 2 millitesla. So let's say the magnetic field is going this way. And the field strength is, it's a uniform magnetic field. So B is constant. B is 2 milliteslas. That's going to be what, 0.2 times 10 to the negative 3 teslas? Yep. Okay, so let's think about that. Our formula for EMF induced in a coil, right, is... Where is it? EMF equals minus N, change in magnetic flux over time. So EMF equals minus change in magnetic flux over change in time. So magnetic flux, let's just rub that out. Magnetic flux is how many field lines are passing through this. Basically, that's what it's a measure of, and I think it is BA cos theta. And that is that's the perpendicular angle that the rectangle makes with the field. So right now, let's say we've got a perpendicular coming out of the loop, like the normal vector. I don't know if you guys do specialist. 90-degree angle. So it's this angle, the angle between the perpendicular and the field. We said B is going that way. So if that angle's 90 degrees, cos of 90 is 0, so magnetic flux is 0. The way I've drawn this, say I've put the field is going this way, and I've just got this thing here. None of the field is going through the rectangle. So this is when magnetic flux is at a minimum. So it's at a min when the perpendicular angle is 90 degrees. It's going to be equal to a maximum then. Let's draw our field again. So it's going to be equal to a maximum when it's like a window now. These guys are going straight through the window. The angle that the perpendicular to this, kind of hard to draw, is making with the field is 0. It's 0 degrees. So it's at a maximum when the angle is at 0 degrees. Now, EMF, our average EMF produced over some amount of time. They're telling us 6 volts. So, and the change in magnetic flux is going to be the change in this as the angle goes from 90 degrees to 0 degrees. So let's go a bird's eye view, right? That's our square. That's our square. We're viewing it from top down. And that's the square again, and we're rotating it by 90 degrees, right? And our magnetic field is coming in this way. So when it's parallel to the field, none of the magnetic field is going to get through. Once we rotate it, it's all going to get through. So that's maximum, magnetic flux. So our change in magnetic flux is going to be, well, we know A is 0.1, B is 2 times 10 to the negative 3. Let's say this is when it's at its minimum. So at its minimum, the magnetic flux is 0, right? Because none of the magnetic field is getting through. At its maximum, it's going to be BA cos theta. So 2 by 10 to the negative 3 times area, 0.1 by 0.2, cos, and the angle is 0 degrees, right? So that's just 1. Cos of 0 is 1. Let's pop that in. So that's 4 by 10 to the negative 5. What is that, Webers? So in other words, our change in magnetic flux as we rotate 90 degrees in this, it's spinning at whatever RPM, is 4 by 10 to the negative 5 Webers. Now we need to figure out, okay, what is the change in time? Because the time is going to give us it's going to be related to our RPM. So RPM, revolutions per second, sorry. Let's just say RPS. It's just going to be number of revolutions per second. Now let's say the time for one revolution. So in other words, if this guy was to rotate 360 degrees, let's say the time that would take would be capital T, right? It's going to take capital T seconds to rotate 360 degrees. So I hope you can see if we're rotating at a constant speed, then it's going to take us 1/4 of that time to rotate 90 degrees. So, 1/4, 1/4, 1/4, 1/4, 1/4 T. So if it takes us T seconds to do one revolution, T seconds, or we can say revolutions per second is going to be 1 revolution over T seconds, right? So, with all that in mind, let's go back to this formula. EMF equals change in magnetic flux over time. 6 volts, average EMF. It's going to be negative 4 times 10 to the negative 5. I don't think the negative is important here. Over the change in time from here to here is 1/4 T, right? 1/4 T, we just figured that out. So let's divide that by 1/4 T. And this is a case where I'm going to do solve n because that looks really uncomplicated. 6 equals, I'm going to ignore the negative, 4 by 10 to the negative 5 on 1/4 times T, x. So that gives us T equals 1 on 37,500. So revs per second is going to be 37,500 revs per second, which just does not sound right. Okay, let's clear our heads. We got 1 hour left and we're still on multi-choice number 13, so we might have to pick up the pace a bit. EMF equals negative change in magnetic flux over change in time. Now, we said our change in magnetic flux happens as the angle, from bird's eye view, changes from 0 degrees to 90 degrees, right? Or should I say 90 degrees? The angle of the perpendicular changes from 90 degrees to 0 degrees. And it takes us 1/4 t seconds to do that. Now, we know revs per second is 1 on t. And we know the time taken to move from 90 degree angle to 0 degree angle is 1/4 t. So our change in magnetic flux, if we started at 0, the absolute value of that change is going to be BA cos theta. 2 milliteslas. 2 milliteslas. Oh, 3,000 turns? I forgot the N. Forgot the N. I think that's important. Yeah. Okay, apparently it's been too long. So EMF is minus N times the rate of change of magnetic flux. Now this N is turns per... Is it just number of turns or is it turns per meter? Let's just say N is 3,000. I don't even know what N means, but like exam strategy, we're just going to have to get this one done. It's going to be minus 3,000 times, and our change in magnetic flux, let's use the number we had before, minus 4 by 10 to the negative 5 on 1/4 t. Oh, and that's going to be a solve n, so 6 equals that. EMF equals 6. So that's now saying T is 2 on 25, which is promising. So what I changed there from my previous answer, I forgot the N in this formula, and I'm just assuming that N is number of turns in the coil. So that's given me 2 on 25. So revs per second is going to be 1 on t, which is 25 on 2, or 13.5. So I'm going to go C for 13. We might need to come back to that one. That was tricky. Okay, this one seems straightforward enough. Neutron decay. So if a proton is what, up? Is it up, up, down? No, it's sorry, a neutron's definitely up, down, down. Yeah, and a up, down, down. Now, if a neutron decays into a proton, that's going to be up, up, down. So we've got up, down, down coming in. We need up, down, up coming out, or up, up, down. We've got up, up, down coming out. So it could be this one, and it could be this one, but it can't be D, because we've just got a neutron turning into a neutron by the looks. There's no decay happening. So let's look at these two. If a neutron is becoming a proton, it's gonna be like ejecting negative charge, if that makes sense. To become positively charged, it's not going to give off positive charge. That's my reasoning, at least. It's going to have to give off negative charge to, like, lose some negative charge and become positively charged. So C. I'm just going to go with that one. We might have to come back to this. Let's pick up the pace a bit. We got 1 hour and 3 minutes remaining. An object's velocity can only be measured relative to a fixed reference frame. Yeah, the speed of light. Maybe? No, we measure the speed of objects relative to each other. If I'm running at, 1,000 kilometers per hour relative to the Earth. Yeah, let's say a fixed reference frame. Which option represents the resultant vector of x plus y? This is a great calculator one, guys. Your calculator is so good at this. So I'm going to convert 35... no, you know what? Screw it. We're just going to do a good old... we're just going to do horizontal component sum, vertical component sum. So the sum of the horizontal components, 35 cos 40, plus, you can see the horizontal component is still positive, 48 cos 60. So that's like 50.81 is our horizontal component. Now vertical component here is positive, here it's negative, we can see that. So it's going to be 35 sine 40 minus 48 sine 60. So vertical component is minus 19.07. Now the angle we can find, it's going to be the inverse tan of x on y. So if we think about that, we're looking for this angle. We've got x here and y there, right angle triangle. Tan of theta is opposite on adjacent, y on x. So theta is going to be inverse tan of y on x. Let's just go 19.07. It's the negative angle, of course. 50.81. So that's giving me 20.6 degrees. 20.57. And that's obviously coming down onto the horizontal. So 20.6 degrees, that's the only one with that angle. Now our magnitude, let's just double check that, is going to be root of x squared plus y squared. 50.81 squared plus 19.07 squared. 54.3. Okay, that's right. Question 17. An object is in orbit 400 kilometers above the surface of the Earth. The Earth has a radius of 6.4 by 10 to the 6 meters. What is the magnitude of the gravitational field strength experienced by the object? Jesus. So gravitational field strength, we got that little g, and it's going to be equal to gm on r squared. So looks like they've given us all the information we need. 400 kilometers is our radius, so let's put that on the denominator. 400 kilometers, kilo times 10 to the 3, right? Yep, 400 by 10 to the 3 meters. Big G. 6.67 by 10 to the negative 11 times mass of Earth, which we did before. That's 5.97 times 10 to the 24. That's looking like nothing that's on there. What have I done wrong? Oh, I didn't square the radius. So we've got to square that radius on the bottom. 2488, so 2.5 by 123 by 10 to the 3. Okay, primary and secondary coils from a lossless transformer are shown. Now, God, all right. EMF, we just did this. It's going to be, it's proportional to the number of turns, n. So this one has less coils, this one has more coils, so presumably EMF is going to be lower here and higher there. It's going to experience higher voltage, EMF voltage going up because it's directly proportional to the number of turns. But if voltage goes up, then current is going to have to go down. We can't just create energy out of nowhere, you know, V equals IR, whatever. If voltage goes up, that's going to have to go down. So it's going to experience decreased current. Perhaps, you know, you could say, oh, why doesn't resistance go down? Perhaps the better formula to use is power is voltage times current. Now, we can't invent power out of nowhere for the power to stay constant. If this increases, that's got to decrease, if that makes sense. Question 19. A current carrying wire is placed perpendicular to two magnets. As the current in the wire is changed, the force acting on it is recorded. The gradient of the line of best fit is proportional to the... Okay, we've got a force current graph. Gradient equals, let's just do F on I, force on current, or change in F on change in I, which is just the ratio of that, which should be constant because it's a straight line. Now we are dealing with force on a current carrying wire in a magnetic field, and that formula is BIL, F equals BIL sine theta, current in the wire, length of the wire in the field. So let's write that down, F equals BIL sine theta. So we know F on I. If I divide both sides by I get F on I equals BL sine theta. So in other words, the gradient equals BL sine theta. That's our hack. You know, you can think the change symbols may be cancelled out, but this ratio is constant. It's equal to BL sine theta. So it's proportional to the magnetic field strength, not proportional to resistance of the wire. We don't know anything about that. Nothing to do with electromotive force, nothing to do with potential difference, so it's D. Which option lists the gauge bosons in ascending order of the strength of force they mediate? Okay, so the four forces, we know the strongest is strong force, strong nuclear force. Then it's what? Electromagnetic. Then weak nuclear force. Then gravity. I'm not sure on that one. I'm not sure about that. I'm going to consult my notes. Alright, so we've got standard model notes. Let's have a look. Strong force going from strongest to weakest. Yeah, strong electromagnetic, weak gravitational. So from strongest to weakest, strong electromagnetic, weak gravitational. Alright, that's correct. So strong force is gluon. Gluon mediates that. Electromagnetic photon. Weak nuclear, what's that? W and Z bosons. And gravity, not even part of the standard model. So ascending order of strength means we're going this way. From W, Z boson, photon, gluon. That looks right. Because that's saying weak nuclear force is weaker than electromagnetic force, which is weaker than strong nuclear force. Okay, that's multi's done. I'm not going to fill in the bubbles because that's cringe. A hot iron bar was observed to have a deep red color. As the iron bar was heated further, the color changed to orange. Explain the observed color change in terms of blackbody radiation. Okay. It's 2 marks, which is great, because I don't really know what they want me to say. We know, okay, let's say blackbody radiation is electromagnetic radiation emitted by an object due to its temperature. Wait, that's the definition. Alright. And we know from our formula sheet, where is it? They give us a formula to show us this. As the temperature, T, of the object increases, the maximum wavelength of the distribution of radiation that we emit. So say we've got an object at 3000 K, then its radiation distribution might look like that. I know it doesn't look quite like that. but the max wavelength, so if this is wavelength and that's intensity, this formula tells us, oh, what wavelength is the max of that distribution. And this is telling us, well, as the temperature increases, the max wavelength decreases. So the radiation gets more, has higher energy. Lower wavelength, higher energy. So as the temperature of the object, of the iron bar, let's be specific, of the iron bar increases, the maximum wavelength of the black body radiation emitted decreases. Yeah, more energetic radiation, lower wavelength, decreases. And we know, well, like my thought is, that's got, red has a wavelength of what? Oh yeah, no, that makes sense. It's like 700 nanometers. You do kind of need to know this. And red light is the lowest energy light. Purple light is the highest energy light. It has like 400 nanometers maybe. So if we're moving through the rainbow, wavelength is decreasing. So we can say hence the color of the iron bar changes from red to orange as the wavelength of the visible light emitted decreases. It's 2 marks. Maybe we got the 2 marks, maybe we didn't. Yeah, let's move on. A collection of mesons was observed by a detector to move an average distance of 11 meters when traveling at 95% of the speed of light. However, based on their properties, the mesons were expected to travel an average distance of 3.4 meters. So this sounds like a special relativity question. They're saying they're expecting them to travel a distance of 3.4 meters. So distance is speed times time, right? Therefore, the detector, right, found that the muons, the key word here is based on their properties. So they disagree on the distance, right? The prediction predicted this distance, the experiment showed this distance, right? So the distances are different, but they're agreeing that they both travel at 95% of the speed of light. In other words, they agree that the speed is 0.95 c. Okay, so that means they must disagree about the time. If they disagree about the distance but they agree about the speed, then this needs to be different. So according to the prediction, we're trying to find the difference in time. It's about time dilation, right? According to the predictions, muons, no, not muons, mesons, yeah. Mesons would have an average lifetime t equals so time is what, speed on distance? God, no, time is distance on speed. So the predicted distance was 3.4 meters. on 0.95c. So we can pop that in our calculator. 3.4 distance over speed, 0.95 by 3 by 10 to the 8. So that gives us 1.19 by 10 to the negative 8 seconds, okay? So according to the predictions, mesons would have an average lifetime of that. However, it's moving very fast. So if we're observing these muons, and in our reference frame the muons are moving, then time is dilated in their reference frame. Moving clocks run slow, whatever. So we say, however, because the detector, say, or because in the reference frame of the detector, the detector, the muons are moving. So we can say the detector is moving with respect to the events, so it measures a proper time, a dilated time interval. So because the muons are moving at relativistic speeds in the reference frame of the detector, the lifetime of the muon, the average lifetime, is dilated. Let's just, in general, if you're stationary and a particle is moving really fast, then you're going to measure a dilated average lifetime of that particle. It's dilated, so we'll say t equals it's the gamma factor, so gamma t0, t0. We'll call that t0. That's proper time. So gamma factor is what? Or we can use our formula. T0 is going to be, it's decrease. It is, do we divide by gamma? Yeah. If we're dividing by gamma, is that... No, we're multiplying it by gamma. Sorry, yeah, we are multiplying it by gamma. Gamma is 1, right? 1 on 1 minus v squared on c squared. So that's 0.95 squared on 0.95 squared on 0.95 squared c squared. No, sorry. So v squared is 0.95 squared c squared, right? Because we've squared 0.95c. On c squared, the c's squareds cancel out. Times, t0, 1.19 by 10 to the negative 8. Okay, not the cleanest working out, but... So, it's going to be 1 on that. You could just use the formula, right? You could just say t equals t0 divided by this, which is what I'm doing. I'm saying it's 1 on this times t0. 1 minus, because the c squareds cancel out, it's just 1 minus 0.95 squared times the proper time. So 3.81 by 10 to the negative 8 seconds. So the distance observed, and distance is speed times time, is 0.95 c times 3.81 by 10 to the negative 8, which is 0.95 by 10 to the 8 by 3.81 by 10 to the negative 8, which is 3.61. It's not quite 3.4. Yeah. It's okay, it'll do. Just say 3.6. I'm struggling. 3.62 meters. Let's just say that's approximately equal to 3.4 meters. Maybe they didn't want a quantitative explanation, sorry. Maybe they just wanted me to say the time is dilated, so the distance traveled decreases if distance is speed times time. But whatever, we're moving on. Oh, these ones. Okay, I think this is the Rydberg thing. So this diagram shows the electron energy levels for hydrogen. Calculate the energy released in joules when an electron moves from the third to the first energy levels. Show you're working. This is pretty simple. This is Rydberg. What's his thing? Quantum theory. This formula. So final energy level, initial energy level. This formula, let's write it down. 1 on wavelength, yeah, is going to be equal to R 1 on NF squared minus 1 on NI squared. So that's when we move between energy levels, when we move from a higher energy level to a lower energy level, a photon is given off. So this is the wavelength of that photon. If we know the wavelength, then we can calculate the energy of the photon, which is what they're asking for. E is hc on wavelength. So let's start by calculating 1 on the wavelength. Rydberg's constant is R, capital R, 1.097 by 10 to the 7. So it's going to be 1 on, if final is first, 1 on 1 squared minus, oh god, hang on, no, I'm being stupid. I'm being really stupid. They've given me the energy. This is why I'm doing this, guys. I got to study too, all right? I got to study too. So we're moving from, my apologies, we're moving from this energy level to this one, right? So the change in energy is going to be equal to the energy that we give off. Change in energy is going to be final energy minus initial energy. So 12.09. I'm going to ignore the negative electron volts, which is going to be 12.09 by 10 to the, no, 1.6 by 10 to the negative 19. That's your conversion. So negative 1.9344 by 10 to the negative 18. Going to ignore the negative. I think what the negative means is the energy of the atom went down, the system that containing the electron and the nucleus, that energy went down. So energy was released. Change in energy was negative. 1.934 by 10 to the negative 8 joules. Go with it. Explain why hydrogen only has 4 emission spectrum lines in the visible spectrum. God, I saw this one in Perusal and I was like, what the hell? What the hell? Why? Why does it only have 4 emission spectrum lines in the visible 400 to 700 nanometer spectrum? Don't ask me. I'm thinking, okay, this is, what is it? I think it's the Balmer series. Balmer series is the visible one. And that is when atoms are, you're heating up your, hydrogen gas, and the atoms in the first energy level get excited and move up, so they absorb energy, and then they move back down to the first energy level? Hydrogen's got one proton and one electron. So that electron is moving up an energy level, up an energy level, up an energy level, then coming back down. I'm gonna read the notes on this one. Okay, we've got what have hydrogen produces infrared, visible, and ultraviolet emission spectra. Dark lines, yeah, okay, we know that. The visible series of the hydrogen line spectrum is now known as the Balmer series. These lines have a similar whatever. Yeah. Okay, maybe we mentioned something about the Bohr model of the atom and the fact that hydrogen has one proton and one electron. And the fact that when an electron is moving between stationary states, it gives off a proton, God knows. Ah, hang on, this is it. Okay. The Balmer series is in the visible region corresponding to transitions to the n equals 2 level. So the final energy level is 2 and the initial energy level is 3, 4, 5, and 6. Let's write that down. Maybe they want us to memorize that. The 4 emission spectrum lines, or the 4 hydrogen emission spectrum lines in the visible region, let's just say like 400 to 700 nanometer region, are known as the Balmer series. I've just got Will in the chat saying, I think the negative means, so from the question we just did, I think the negative means the system must do negative work to move an electron from a higher to a lower energy level, i.e. the system does work so it loses the ability to do work. True. Yeah, the system lost potential energy. That makes sense. Yeah. If the system lost energy, the change in energy of the system was negative, but the energy released was positive. Yeah, okay. Okay, visible region, Balmer series. What did I just say? These lines correspond to the wavelengths of photons emitted when... Actually, before we say that, hydrogen has one proton and one electron. Yes, Will. I am a serious guy. Yeah. Hydrogen has one proton and one electron. These lines, the spectral lines, corresponds to the wavelengths of photons emitted when the electron transitions from a higher energy level. A higher energy level. And we'll just write n equals 3, 4, 5, 6. So these lines are caused when, say the electron is in energy level 3, 4, 5, or 6, it's moving back to energy level 2. Transitions from a higher energy level to the lower energy level, n equals 2. I don't know what this question wants me to say. Does hydrogen have 4 energy levels though? Like, couldn't you keep exciting the electron further? So Will's just said, am I oversimplifying? Or is it just asking you to say that hydrogen has 4 energy levels? Could I, if I kept exciting it, then say I went from energy level 7 to 2, then I would just have a higher wavelength, or sorry, a lower wavelength. So it would be out of the visible spectrum. I don't know, we'll see the marking guide and what they wanted us to say. Correspond to the higher energy level because these wavelengths are within the visible spectrum. There are only 4 lines. Because these wavelengths are within the visible spectrum, while the wavelengths produced by other transitions are not. Did I do the magnetic flux rotation question? I did. I got 13. Might come back to it. We'll see, we got 30 minutes. These wavelengths are within the visible spectrum, while the wavelengths corresponding with smaller or larger transitions are not. There are only 4 lines in the 4 emission spectrum lines in the visible region. That's, yeah. So Zach's just said, you can also prove part B using the other formula to further help your answer. That's what Rudkin showed me. E equals CH on Flander. Yep, HC on lambda. Yep. I think I get what he's saying. Oh, yes. Yes, I get what he's saying. So Zach's just made a point. They've given us these energy levels, right? Now the 4 transitions in the Balmer series, they're caused by 3 to 2, 4 to 2, 5 to 2, and 6 to 2. We can calculate the change in energy and then calculate the wavelength to show that that is within the 400 to 700 nanometer region. So let's calculate those wavelengths. So we've just said the 4 hydrogen spectrum lines in the visible region are known as the Balmer series. Hydrogen has 1 proton and 1 electron. The spectral lines correspond to the wavelengths of photons emitted when the electron transitions from a higher energy level, 3, 4, 5, 6, to the lower energy level, n equals 2. These correspond with Where's my rubber? Don't have one. Let's write over it. So these transitions correspond with the following wavelengths. Or do we really want to be calculating 4 of them? Or are we just going to calculate the biggest one and say that's outside of the visible spectrum? So in other words, let's calculate 6 to 1, and that's going to be outside of the visible spectrum. And then if we calculate 6 to 2, that's going to be inside the visible spectrum. And then we'll say, so the transitions are 3, 4, 5, 6, and not to n equals 1, if that makes sense. I'm going to move on though, and come back to that one. A rectangular loop is placed in a uniform magnetic field of 5 millitesla. Okay, that's fine. We're looking for change in flux. So initially it looks like the angle that it's making with the perpendicular of the field. So field's going from north to south. And the perpendicular angle is 90 degrees. So initial angle is 90 degrees. Let's just show initial. So initial magnetic flux, BA cos theta, 5 by 10 to the negative 3 millitesla. Yeah, so 5 by 10 to the negative 3 times area, 0.2 by 0.3, times cos of 90, which is 0, so it's just going to be 0. Now the final, if we're going from an angle of 90 degrees, and we're rotating it this way, so 90 plus 60, the horizontal, so the perpendicular of the loop is now going to be here, and it's been rotated 60 degrees is the change in angle. So it's going to be making an angle of 30 degrees with the field, if that makes sense. If I was at 90 degrees, if the perpendicular of the loop was at 90 degrees to B, and I've just rotated it 60 degrees, then B is now at 30 degrees to the field. So two sig figs, that's 2.6 by 10 to the negative 4. Webers. Sorry about that, and then let's just say therefore the change in magnetic flux is 2.6 by 10 to the negative 4 minus 0. Describe how electromagnetic radiation is propagated by the interaction between electric and magnetic fields. So that's our whole oscillating electric field creates oscillating magnetic field. Let's say electromagnetic radiation is produced when an oscillating I'll start with an oscillating electric field. It's produced when an oscillating electric field I'm just going to say induces, because or via electromagnetic induction, maybe. So an oscillating electric field creates an oscillating magnetic field, which in turn creates an oscillating electric field. So by the process of this is a trash answer, by the process of electromagnetic induction. Hence, the electromagnetic radiation is self-propagating and does not require a medium. It's a particle decay. List 2 types of particles whose total number must be conserved in this reaction. That's an easy mark. Conservation of lepton number means the number of leptons is conserved. Conservation of baryon number means the number of baryons is conserved. So I'm just going to say leptons, and then in brackets I'm going to put electron. No. No, yeah, I'll just say leptons, and because it's the leptons are the electron and the anti-electron neutrino, so +1 plus -1 gives you 0, and there's 0 on this side. And baryons. Let's just say that. Object A is 5 times the mass of object B. The graph shows the contribution of each object towards the strength of the net gravitational field between them. Determine the total distance between the center of the 2 objects. Show your working. Well, immediately I'm kind of going, oh, there's a point of intersection here. So something is going to be equal to something at that point. The gravitational field strength. Object A is 5 times the mass of object B. To the strength of the net gravitational field between them. So in other words, this line here is it's the contribution of A to the gravitational field strength, to the strength of the net gravitational field. So where's my G? I think they're saying the gravitational field strength due to A, which is this line, so GA is equal to Gm on R squared, where m is the mass of A. So we know object A is 5 times the mass of object B. Let mass of A, A equal 5m. So mass of B equals m, right? So it's going to be G times 5m on R squared, right? Because mass of A is 5m. And then GB, so gravitational field strength due to B, G times m on R squared. Now, at this distance from the center of A, they are equal, and they are both equal to, I don't know what that number is. Perhaps we're better off going... No, it doesn't really matter what they're equal to, just the fact that they're equal to each other. So if I was to draw a diagram here, we've got A here, and A is pretty big, and then we've got B here. And distance from the center of A, we're going to let that be D, or no, well, we know, so at this point, 30, 2, 4, 6, 8, 40, 32, 34, 35. So at 35 meters from the center of A, or 35 by 10 to the 7 meters from the center of A, sorry, they are, GA and GB are equal. So this is our point in the field. We're saying this distance, 35 by 10 to the 7. Now we're looking for the distance between them. So this total distance, this whole distance, let's just say that's D. That's what we're trying to find. And it's the center of the two objects. So we're just going to assume the radius is nothing, if that makes sense. So this distance here is going to be D minus 35 by 10 to the 7 meters, yeah? Now, when when the distance from the center of A is 35 by 10 to the negative 7, let's calculate GA, right? So GA equals GB when 35 by 10 to the 7 meters away from center of A. So G times 5m on, we're here in the field. Our radius to A is this. It's just that, 35 by 10 to the 7. So 35 by 10 to the 7 squared equals G dot M on, because that is GB, so it's equal to GB. And the radius from B is D, the distance between them, minus 35 by 10 to the 7, if that makes sense. So D minus 35 by 10 to the 7 squared. Now, immediately we can cancel M, and we can cancel G. So we're saying 5 on 35 by 10 to the 7 squared is going to be equal to 1 on D minus 35 times 10 to the 7 squared. Maybe I'll try solving that. This is the kind of thing where solving is sometimes a bit dodgy. Yeah, they're saying there's no solution. So let's cross multiply. I reckon I can solve that. Alright, so I've solved and that. Just say solve using GC. Maybe the marking guide will want you to solve it yourself. We'll have a look when we mark it. But it's saying the two possible distances are that and this. So let's just write those down. 1.1, 2, 3, 4, 5, 6, 7, 8. And like 1.93 by 10 to the 8. 1, 2, 3, 4, 5, 6, 7, 8. And then 5.07 by 10 to the 8. So how are we going to choose which one is correct? Well, we could sub in, say we sub it back into this. So G dot 5m should be equal to G dot m on d minus that. So let's just check if left-hand side equals right-hand side. Yeah, look, I'm just going to move on. We're going to figure that one out when we mark it. Oh dear. An object of mass 200 grams moves in a uniform circular path with a radius of 25 centimeters. The time taken for 10 revolutions is 3 seconds. So we want to find the period. So this is a v equals 2 pi r on t thing. We want to find t, time for 1 revolution. So the time for 10 revolutions is 3 seconds. 3 seconds, 10 revolutions. Time for 1 revolution is just 3 divided by 10, 0.3. So 0.3 seconds per rev, if that makes sense. And then 2 pi r, well, we've got our radius, 25 centimeters. So 2 pi times 0.25 meters on 0.3 seconds. And that is equal to 5.24. 5.24, sorry, just looking at the chat. Meters per second. So the distance is speed times time, which is going to be 5.24 times 3.9. Which is like 20.436 meters, which is just 20 meters to 2 significant figures. Centripetal force. What's our formula for that? Circular motion? Where is it? Oh. Well, centripetal acceleration is v squared on r. Hang on. Net force is what we're looking for. F net equals mv squared on r. It's 200 grams, 0.2 times 5.24 squared on the radius is 0.25 meters. Eight point four newtons. 8.4. That's it. Let's go back. Let's think real quick. Where did I go wrong? You would think it could be both because Okay, let's just think about this real quick. The gravitational field strength due to A is bigger than the gravitational field strength due to B as we move away from A. And this point, because A is a bigger mass, right, this point needs to be further than halfway, because A is stronger. So A is a bigger mass. For the gravitational field strength to be equal, we can't be halfway in between. We're going to need to be more than half the distance away from A. So let's check that. We've got these two distances. So let's just say because mass of A greater than mass of B, need to be more than half the distance away from A to have equal gravitational field strength. So is 1.93 by 10 to the 8 minus 1 by 10 to the 8 minus 35 by 10 to the 7. Well, I think that explains it. Doesn't have anything to do with this. Okay, so to check our reasonableness, both of these distances need to be positive. You can't have a negative distance. 35 by 10 to the 7 meters away from A, perfect. We need to be a positive distance away from B. I've just subtracted 35 by 10 to the 7 from 1.93 by 10 to the 8. And it's negative because 1.93 by 10 to the 8 is in fact bigger. Oh, sorry, 35 by 10 to the 7 is bigger than 1.93 by 10 to the 8. Whereas 5.07 by 10 to the 8 minus 35 by 10 to the 7 is positive. Too easy. So let's just say D equals 5.07 by 10 to the 8 as 1.93 by 10 to the 8 is less than 35 by 10 to the 7. D must be positive. Or just not D, like all the distances. Distances must be positive. So just going to pop that in there. 5.07 by 10 to the 8. All right, let's go back real quick to that one we sort of screwed around with. I'm going to do this on a different sheet of paper. We got 3 minutes to do it. Okay, speed run. The 4 hydrogen emission spectrum lines in the visible region are known as the Balmer series. Hydrogen has 1 proton and 1 electron. The spectral lines correspond to the wavelengths of photons emitted when the electron transitions from a higher energy level to a lower energy level. Now from part A, the smallest transition involving the first energy level is the transition from 2 to 1, so E 2 to 1, which is final minus initial minus 13.6 minus 3.4. 10.2 EV, which is minus 10.2 times 1.6 by 10 to the negative 19. It's like minus 1.632 by 10 to the negative 18 electron volts. This would correspond, no, not electron volts, joules. This would correspond with a wavelength of, so if E is hc on pi and hc on lambda, then lambda is hc on E, which is going to be I don't think we're going to have time for this one. Do it anyway, just for learning purposes. So 6.626 by 10 to the negative 34 times 3 by 10 to the 8 on 1.632 by 10 to the negative 18. Yeah, that's our time. That's our time. I'm just going to finish this question. Okay. So, 1 point. I don't really think I'm doing the right thing here. If I think I'm using the wrong formula. So the smallest transition involving the first energy level is, yes, it is this one, E2 to 1. Or let's just say it's n equals 2 to n equals 1. And the wavelength associated with it is the wavelength of the photon emitted is, so 1 on lambda equals R1 on n f squared minus 1 on ni squared. So that is the Rydberg thing in your data book. That's saying if I go from 2 to 1, then 1 on the wavelength of the photon emitted is that. So 1.097 times 10 to the 7. Oh, sorry, times 10 to the 7. 1 on 2 squared minus 1 on 1 squared, right? And I'm just going to put that all to the power of -1 because that's 1 on wavelength. See, that's not what I meant. I might have to give up on this one. Yeah. How did I go wrong? Hang on. Oh. No, that makes sense. So that's saying wavelength is equal to negative. Just going to ignore that negative. 1.215 by 10 to the negative 7 meters. Right? So that's that is 121.5 by 10 to the negative 9 meters, which is 121.5 nanometers outside the visible spectrum. Thus, the transitions in the visible region must involve, or must not involve, n equals 1. The remaining transitions are I really can't be bothered with this one. The remaining transitions are 3 to 2, 4 to 2, 5 to 2, and 6 to 2. Which, hence there are only 4 in the visible spectrum. Yeah, I'm sorry. Let's mark it. What do we get? How do we go? I've got the marking guide here somewhere. For the other formula, if you sub in your visible wavelengths, you can work out the required energy. Zach, you're a genius. I get what he's saying. At last. So he's saying if you want a photon in the visible, or so for the emitted photon to be in the visible region, wavelengths must be between 400 and 700 nanometers, right? So energy, lowest change in energy that you can have is going to be hc on lambda. So what, 6.626 by 10 to the negative 34 h times 3 by 10 to the 8 c on lambda, 400 by 10 to the negative 9. So lowest change in energy you can have is 4.9695 by 10 to the negative 19 joules, which is going to be that divided by 4.9695 by 10 to the negative 19 on 1.6 by 10 to the negative 19. We're going from joules to electron volts. It's going to be 3.11 electron volts, right? That's going to be the greatest change in energy, because lowest wavelength, greatest change in energy. So highest change in energy, lowest change in energy that we can have to produce a photon in the visible spectrum is 700 nanometers. 6.626 by 10 to the negative 34 by 3 by 10 to the 8 on 700 by 10 to the negative 9. Let's change our number. So that's 2.8397 by 10 to the negative 19 joules, which is equal to that divided by 1.6 by 10 to the negative 19 electron volts. 1.77 electron volts. So in other words, our transition must be between, so the change in energy between the energy levels must be between 1.77 to 3.11 electron volts. Now, let's calculate 2 to 1, right, which is what we calculated before, is going to be, we'll just ignore the negatives, 13.6 minus 3.4, 10.2. So, thus, the final energy level is not n equals 1, because the smallest transition produces a photon with energy far in excess of the visible region. So let's calculate instead energy level of 3 to 2, which is going to be 3.4 minus 1.51, 1.89 EV. This is within visible region, because that's bigger than 1.77. So 4 to 2 is going to be 3.4 minus 0.85. 3.4 minus 0.85. Uh, 2.55. And E5 to 2, 3.4 minus 0.54, 2.86, 5 to 2, and 6 to 2. .02 electron volts. All of these, so let's just cross that out and say, therefore, all within visible region. Now, that's 4 that are within the visible region. I hope you can see that if I went from if I went from 4 to 3, that would be too small. I don't exactly know how they want you to explain that, so I'm just going to leave that there. No. Starting at finishing at n equals 3, so if n equals 3 was the final, it'll just make some statement to that effect. If n equals 3 was the final energy level, then the photon energy would be too low. Okay, marking guide. Where'd I put it? Let's do the multis. So B, C, A, B, B. B, C, A, B, B. Yep. A, C, C, B, A, C, B. I got that one wrong. So that's question 9, B. Oh no, that's right. B, A. Question 10, yes. 11, D, A, C, C, D. D, A. I got this one wrong. So question 12. No, that is correct. D, A, C, D. Question 14. C, 15. D. Okay, so 15, the answer was D. An object's velocity can only be measured relative to an observer. I'll just note that down when I got one wrong. A fixed reference frame. I guess, like maybe they're saying the reference frame can be moving. Like, I don't know exactly what fixed reference frame means. Yeah, Will's just said the frame of reference can be moving. Cool. I guess by fixed they mean stationary. Yeah, the reference frame can be moving. I guess an object's velocity can only be measured relative to an observer. That does make sense. An observer needs to measure it. Whether you're saying, oh, the velocity of me relative to the Earth, then what you're really saying is the velocity of me relative to an observer standing on the Earth. And none of the other ones make sense. So, yeah, I guess that makes sense. You need someone to observe your velocity. You're measuring it with someone. You're measuring it with respect to someone or something. Let's just check these other ones. 16D, 17A. Oh, looks like we've got 17 wrong. What have we done there? So 400 kilometers above the surface of the Earth. Magnitude of gravitational field strength. I'll go back in my calculator. So I've gone G, 6.67 by 10 to the... Ooh. Never mind, I'll have to calculate it again. So 6.67 by 10 to the negative 11, that's big G. I didn't add the distances. Right. So Will's just said, I've basically assumed the radius of the Earth didn't exist, when really, so here's our object, here's the distance, 400 k's, 400 by 10 to the 3, and then the radius of the Earth is actually bigger, 6.4 by 10 to the 6, so the total distance between the object and the center of the Earth, if you will, is those two added together. Thank you, Will. So 6.67 by 10 to the negative 11. That's big G. Hold on, there's my data book. mass of the Earth, so GM, mass of the Earth is 5.97 by 10 to the 24 kilos, and then R squared, he's just pointed out, R is really 400 Ks plus 6.4 by 10 to the 6 meters, which is the radius of the Earth, squared. That gives you 8.6 by 10 to the 0, which is a, so we got that one wrong too. 17 was supposed to be A. 18B, 19, D, 20, D, nice. Short response. Alright. Question 21. Oh yeah, this will be interesting. So they have, in their marks guide, describes the scenario in terms of blackbody radiation, 1 mark, uses Wien's law to explain the color change in the iron bar. We sort of did that. We didn't state the formula. So we've described the scenario in terms of blackbody radiation, sort of. We did say, okay, so we did say as the temperature increases, we said something to this effect. The peak wavelength will be shorter, and this is observed by the color change from red to orange. But I really should have said, according to Wien's law, and then stated Wien's law, lambda max equals B on T. Right, I should have said that to get the Wien's law mark, probably. I probably, I could have been a bit clearer about the fact that the iron ore has a color is the blackbody radiation. So I'm probably not, I'm going to give myself 1 out of 2 there. So what I should have said, a more ideal answer would have been the color of, the glowing color of the hot iron bar is due to blackbody radiation. Sure. The glowing color is due to the blackbody radiation because it's the radiation emitted due to the temperature. It's just basically pointing out the iron bar is not red. The reason it's red is it's glowing red because of its temperature. So yeah, 1 out of 2 for that. Thanks for the encouragement, guys. Question 22, 2 marks. The relativistic speed of the mesons identifies that an object at relativistic speed experiences time dilation. We did do that. We said because the muons are moving at, I said muons. That should be mesons. Are moving at relativistic speeds in the reference frame of the detector, the average lifetime is dilated. Yes. Explains the relationship between time traveled and observed distance. The mesons appear to travel for a longer period of time and hence cover a larger distance. We did calculate that. They weren't looking for calculations. They were looking for a qualitative explanation. Yeah, so we'll give ourselves 2 marks for that. electron energy levels for hydrogen. What did they say? So we've got the first part right, 1.93. I probably wouldn't get the mark for this because oh no, to 3 sig figs, yeah. I've done it to 4 sig figs because I'm an idiot, but 1933, not 4, so I'll just give myself the mark for that because I'm feeling sad. Determines the energy released, converts it from electron volts to joules. Recognizes that it's the change in energy. So that's 3. This is interesting. So our part B, we'll be on the piece of paper, uses the relationship between emission lines and orbital energies. So they didn't require you to calculate anything in the marks guide, but emission spectrum lines relate to the wavelength of light produced by the release of energy as an electron moves from a higher energy level to a lower energy level within an atom. So correspond to the wavelengths of photons emitted when the electron transitions from a higher energy level to a lower energy level, sure. Since the visible light spectrum corresponds to wavelengths between 400 to 700 nanometers, only energy emitted with wavelengths within this range will be observed. This corresponds to electrons moving between levels where n equals 2, 3, or 4. So get a mark for that, for saying the emitted photon needs to be in the visible region, so the wavelength is 400 to 700. But emission spectrum lines relate to the wavelength of light. Identifies specific aspects of the energy level diagram. I mean, yeah, we calculated those. You don't even need to calculate them, you just need to say, I've looked at the diagram. Based on the diagram, there's 4 changes in energy that produce a wavelength, or even better, there's 4 changes of energy that are within that range. And you don't even need to calculate them, you can say, so to be in that range, you can just state it's 3 to 2, 4 to 2, 5 to 2, 6 to 2. Everything else is outside that range. So only 4. I'm going to give myself 2 out of 3 for that. So 5 out of 6 for that question. Um, 24. So this is the rotating thing. 2.6. Yeah, the important thing there is the angle of 30 degrees. So we identified that, or even we drew it on there. Amount of magnetic flux passing through an area. Sure. Calculates the change in flux, yep. Oscillating charged particles induce a magnetic field. This subsequently induces an electric field perpendicular to the magnetic field. I didn't use the word perpendicular, so I should have said, I just should have said perpendicular somewhere. Oscillating charged particles induce a magnetic field. Yeah. So I think what they want you to go, I did describe the production of an induced magnetic field, but they wanted your line of reasoning to be oscillating charge, which creates magnetic fields, which then creates electric field. And you needed to say they were like mutually perpendicular. That's fair. That's fair. So you get 1 out of 2 for that. This one though, we got the easy mark, baryons and leptons. I'd be interested to see the reasoning for this one. Identify the scenario relates to gravitational field strength. Yeah, so we got the GA equals GB, which is what they were looking for. Identifies distance from A where net gravitational field strength is 0. In other words, where they're equal. We did that. We said 35 by 10 to the 7. Constructs an equation that can be solved for the distance between the objects. Yes. By cancelling. Provides appropriate mathematical reasoning. Maybe, because we solved. And then I guess the appropriate mathematical reasoning part would be where we selected this answer. 1, 2, 3, 4. And then the correct distance, we got it, but again, instead of doing 2 sig figs, I've done 2 decimal places, but whatever. Should be 5.1 by 10 to the 8, 51 by 10 to the 7. 20 meters? Yeah, okay. 22 newtons. That's not right. They've done the calculation I did. Let's have a look. So 0.2 on 3 point... Oh. I used... What did I use? I said 3.24 instead of 5.24. So maybe there's a follow through for that. Get the 2 marks for that though. Why on earth are there 5? Yeah, so they've done the whole thing a bit differently. I did get the velocity correctly. Yeah. I'm just going to go with my correct substitution. Yes. Appropriate mathematical reasoning. Centripetal, well, that's incorrect substitution, but centripetal force, FTE. I'm going to give myself a 6 out of 7 for that, just because I feel like it. Not a great performance, not going to lie. Not too happy with that one. Paper 2. Okay. Let's not do perusal this time, because perusal is for the weak. All right. Two spaceports are stationary relative to each other. Astronaut A moves from one spaceport to the other at relativistic speed and observes the lights on both spaceports turn off at the same time. Sounds like a simultaneity thing. Astronaut B is at a stationary position equally distant relative to each spaceport and observes the lights turn off one after the other. So if I just draw a diagram real quick, here's like the spaceport 1, here's spaceport 2, and astronaut A is moving at like, 0.99 C or something. And he sees them turn off at the same time. So he's moving away from one and moving towards the other. So compared to B, B is equidistant from both of them. So the light from 1 and the light from 2 are going to take the same time to reach B, because he's not moving. But A is moving away from 1 and towards 2. So I suppose we could say he's moving... Yeah, we're going to scrap the notes. Okay, when two events happen simultaneously, they are said to happen at the same time. What may be considered a simultaneous event in one reference frame may not be considered simultaneous in another. Measurement of time in different reference frames produces interesting results, not least for simultaneous events. The idea that simultaneous events happen at different times in different reference frames argues against the existence of any of this one frame. Okay. So consider a light positioned in the center of a train carriage. One end, there's a sensor. Okay. So someone inside the carriage, that's analogous to B. B is equidistant from both of the lights, except in B's frame of reference this time, they're actually turning on at different times. So don't look. From the perspective of astronaut B, the lights are equidistant and stationary. They move the light signals travel at the same speed and reach B at different times. However, A is moving towards one light and away from the other. So yeah, the light the approaching light reaches him more quickly, reaches the astronaut. Guys, I'm so done. More quickly. Hence, events that are simultaneous in A's reference frame are not simultaneous in B's reference frame. Simultaneity is relative. We'll see about that one. Contrast the properties of up quarks and tau particles. Well, up quarks are baryons with a positive 1 on 3 electric charge. They are governed by the strong nuclear force. Tau particles are leptons with a -1 electric charge. They are governed by the weak nuclear force. Well, actually, they are not. Like, are they governed by the weak nuclear force more than they're governed by the electromagnetic force? I'm just going to say they are not subject, not. I'm just going to say they are subject, right? Quarks are subject to the strong nuclear force. Tau particles are not subject to the strong nuclear force. Negatively charged oil drops were placed in a uniform electric field generated by 2 parallel plates. By altering the applied voltage between the plates, the oil drops were suspended in the air between the plates. The graph shows the electric field strength required, achieved by altering the applied voltage, to suspend the negatively charged oil drops between, or varying weight? Okay. So, I guess the idea is, okay, these guys are negatively charged, and we've got them in an electric field of varying strength. If they're negatively charged, then they want to move against the field that way. To suspend them in midair, then the gravitational force down on the drops, so weight force, is going to have to be equal and opposite to the electric force on the drops because they're negatively charged in an electric field. And that electric force is going to be equal to, so it's going to be equal to the repulsive force of the negative against the negative plus the, which is, again, it's going that way, plus the attractive force of the positive on the negative, which is also going that way. So let's write that out. The electric force, and let's call the positive plate A and the negative plate B, and let's call the oil drop X. So the electric force is going to be equal to force on X due to A, the positive plate, plus the force on X due to B, the negative plate. And we can use Coulomb's law there to go, okay, that's K, that's KQQ. So let's say the charge on A is KQA times Q on the drop on R squared plus KQB Q on R squared. Now we can just say that's 2 times KQQ on R squared if we assume the magnitude of the charges on the plates are equal because uniform electric fields. Okay. Now, weight force is just mg. So let's look at what the gradient of that graph tells us. I'm just going to do a rise on run thing. So gradient is 3 minus 0.5 on, and that's by 10 to the 19 as well, divided by run, so 50 minus 10 newtons. Which is 6.25 by 10 to the 17. And that's what newtons per, volts per meter per newton, or ignoring units for a sec. What is the gradient? Well, it is the electric field strength in, let's just say, newtons per coulomb on, oh, sorry, it's just electrical field strength E on force F, right? So the ratio of E to F, change in E and change on F, constant, it's a straight line. So this is, we are talking about the electric force here, Fe, and we know the change in E on change in F equals that. So let's actually ignore what I've just done here and go electric field strength is equal to, or the force, yeah, okay. So electric field strength is equal to force divided by charge, right? So force is equal to, it's equal to EQ. Well, hang on. We just got to start with the gradient, really. So we know E is F on Q. Divide both sides by F. We get E on F equals 1 on Q. So our gradient, in other words, 6.25 by 10 to the 17 is 1 on Q. So let's put that to power negative 1, 6.25 by 10 to the 17, power of negative 1. 1.6 by 10 to the negative 18 is Q. That's in coulombs, 1.6 by 10 to the negative 18. So we've got someone in the chat saying, why is it just, where'd my mouse go? Saying, why is it just 3 minus 0.5 over 50 minus 10? Isn't it just 3 on 50? I mean, you could, that's if you're assuming the y-intercept is at 0. I'm just finding the change in 2 points. But that's fair. Draw a line through the origin. So I'm saying change in y from these 2 points to over change in x, these 2 points. And then someone else has just put wrong. So related maybe? I don't know. Let's think about that. So, I mean, 3 on 50 and that should be fairly similar, shouldn't they? Or 3 times 10 to the 19. Yeah, so you get 6 by 10 to the 17 as opposed to 6.25 by 10 to the 17. Now I'm trying to figure out Hugo Brown. Why am I wrong? Said the electric field strength is the force divided by the charge. Hey, Dweezy man. Still playing Minecraft in class. No. Yeah, I don't know. No, Daniel, you are correct. Thank you, Hugo. Thank you. Okay, another oil drop was suspended between the plates with an electric field strength of 2 by 10 to the 19 volts per meter. Determine the work done to move this oil drop a distance of 5 millimeters towards the negatively charged plate. Show you working. Okay, so at electric field strength equals 2, let's just read this graph here. Using that line that we drew, it looks like 2, 4, so that's 34 newtons. That might be relevant. The work done is going to be the change in electric potential energy. We may not even need to no, yeah, we don't know the distance, sorry, so we will need this. If the force on the oil drop, the weight of the oil drop, sorry, I don't know, is the average charge on the oil drops the same? That's kind of the question here. Because we could say, oh, so each oil drop 1.6 by 10 to the negative 18 coulombs. We're moving that in an electric field of strength 2 by 10 to the 19. We're moving it 5 millimeters towards the negatively charged plate, but then we've also got gravity. So let's calculate the force on the drop, and that force should be constant, right? We've just found the weight force. So we want the weight force plus the electric force on the drop, and then work is force times distance. If the force is constant, we'll just multiply whatever force we calculated by what 0.005 meters. So let's think about that. We know the weight force. It's not even the weight force. No, it is the weight force. So the weight is 34 newtons. And the net force on the drop, remember, it's the electric force going that way and the weight force going that way. So the electric force on a charge of that, remember, F equals EQ. If E is F1Q, electric force is EQ. They've given us E, and we just found Q. So 2.0 by 10 to the 19 by 1.6 by 10 to the negative 18 is going to be equal to 10 to the 19 by 1.6, 10 to the minus 18. Oh, I put a negative in there. 32. So 32 newtons, supposedly. Now, the net force is going to be 2 newtons down. So it's 2 newtons going down, which is great because that's towards the negatively charged plate. So if we're moving it 5 millimeters down, then work equals force times distance, 2 times 0.005, which is just going to be 0.01 joules. God knows if that's right. Yeah. Stationary object on a frictionless inclined plane is connected to a 15 kilogram weight as shown. Calculate the mass of the object on the inclined plane. Okay, so it's stationary. It's just a case of going, all the forces are balanced. We're going to say that the weight going down, so this weight force is equal to the horizontal component of what's pulling that back, and that is going to be the horizontal component of this weight force, right? So you can see if this is, let's call that object A and let's call that object B, it's just going to be the X component of the weight force. So let's just call that like WA or something, weight force on A, and that's weight force on B. And we're saying X component of, we'll actually write that down. So X component of weight force on A equals weight force on B. So F net equals 0, acceleration equals 0. So 35 degrees is that angle, right angled triangle. So that angle there is going to be also 35 degrees. So that horizontal component is going to be mg sine or, you know, let's just say WA equals WAX equals WB, and that's going to be WA sine 35, because it's the opposite side of that 35. Sine 35 equals WB, and then that's mg, so W is mg, where we have an unknown mass, so it's m times 9.8, we know g, sine 35, and we know this one is 15 times 9.8, let's just cancel the 9.8s, and then m is going to be 15 on sine 35, calculate that. 1, 5, 2 sig figs, 26 kilos. Duisman, my goodness, I haven't heard that name in years. Duis Dinkel. The Feynman diagram for a particle interaction is shown. Describe the particle interaction taking place. This looks like electron-positron scattering. You can see electron and positron approach each other in space. They exchange a virtual photon and then sort of depart from each other in space. So we can say, okay, the particle interaction shown is electron, positron scattering. An electron and positron approach each other in space as shown by the converging arrows on on the left side of the diagram at a point. The particles interact by exchanging a virtual photon indicated by the squiggly line. Under the influence of the electromagnetic force. True, Kyle's pointed out Baba, my baby. It's not just electron-positron scattering, they give it a name. Let's call it Baba. Baba scattering. Put electron-positron in brackets. Subsequently, the particles move away from each other in space. Are scattered as shown by the diverging lines on the right of the diagram. They always grayed out in the solution, no need to include it. Okay. Photoelectric effect. A light was shone onto a metallic surface, and then the subsequently released photoelectron passed through a magnetic field. Okay. Identify the direction the photoelectron would have curved, as it passed through the magnetic field. Okay. So, magnetic field going into the page. This is a case of FBI, Fleming's left-hand rule. I'm sure you could use the weird, there's plenty you can use. I'm going to use left-hand rule. Now we can see the velocity is not, the velocity of the photoelectron is not completely perpendicular to the field. Just for the moment, we're going to consider the component that is perpendicular. So if the magnetic field is going into the page, FBI, B is going into the page. And I is, we've got an electron. So So the electron's going that way, but it's an electron, and we're talking about conventional current. So we're going to reverse the direction of current. B going into the page, I going down, F is going to be this way. So the force is only going to be impacted by the perpendicular component of the velocity. So force is going to be this way, and this component of the velocity, the horizontal component, is going to stay constant. It's unaffected. So really, we're just talking about a force going this way. If it's entering the field and the force is that way, then it's going to curve like that. I don't know what term we used. Do we use curve to the right? Do we use curve anti-clockwise maybe? I'm going to say curves to the right, and then in brackets to cover my bases, I'm going to say clockwise, not anti-clockwise, clockwise. Just to get both in case they've got one or the other on the answer guide. The graph shows the maximum kinetic energy of the photoelectron as the frequency of the light was changed. Let's draw a line then. Is that what the marking guide says? Deviate to the right. The graph shows the maximum kinetic energy, so this is the EK equals HF minus W. So what is the gradient telling us? Well, that's change in, so that's the ratio between EK and the ratio between EK and 1 on lambda. They've graphed 1 on lambda, which is interesting because it's not this line. This is, instead of having F on the axis, then yeah, so it's the change in EK over the change in 1 on lambda, which is really equal to the product of EK and lambda. We're saying the product of EK and lambda is constant. You know, you can cancel out the change symbols, is how I like to think about it. So your gradient is equal to this, which is a constant. Now we know the work function is the y-intercept, right? So we're not going to be able to read the y-intercept off the graph. I'm going to have to use this somehow. So let's just start out by going, okay, so EK equals HF minus W, we know that. HC on lambda minus W. Now if we multiply everything by, let's calculate that gradient too. So, rise on run, let's use these 2 points since they're both on there. So it's going to be 1.1 minus 0.2 on run, 2.5 minus 1.8. So it's something like 1.286. Now let's just say I multiply both sides by lambda. So yeah, I'm not liking how this is going. Because say okay, EK lambda equals HC minus W lambda. Then we're a bit stuck, aren't we? Look, maybe I could read the y-intercept. We could calculate the y-intercept at least. So EK equals HF minus W. Let's just start with the y equals mx plus c. Remember, we're dealing with a graph of EK and 1 on lambda. So we know our gradient. So y equals 1.286x plus c, and we're trying to solve for c. Now, we can just pick any point. Let's pick this one, which is y equals 0.2 equals 1.286 times 0.2 equals 1.286 x, which is 1.8 plus c. Now c is not, the y-intercept is not going to be the work function because we're not actually dealing with a graph of ek and f, we're dealing with a graph of ek and 1 on lambda. So I'm just going to do my 1.286 times 1.8, which is going to be 2.3148 plus c minus 0.2. C is going to, it's going to be negative 2.1148. Let's show that. Negative 2.1148. Okay, so in other words, ek equals 1.286 times 1 on lambda minus 2.1148. Now the work function for the metal is going to be the minimum what? The minimum energy required to remove a photoelectron. Oh, scratch this. Alright, I've just had to think about it. The minimum wavelength, we can read that right off the graph, and that's going to be 1.65, or 1 on the minimum wavelength. So from graph, the min wavelength which ejects an electron, and we can see that's the x-intercept, right? So no wavelengths less than this, the wavelengths less than this give you a negative kinetic energy, so no photoelectrons getting ejected. From a graph, the min wavelength that ejects an electron is 1 on lambda equals 1.65. So lambda equals 1 on 1.65, which is 0.61 meters. No, 0. So times 10 to the 6. And then times 10 to the 6. So it's going to be actually a bit different. So it's 6.06 by 10 to the negative 7 meters. Now the work function, so we know work function is hf0, where that's the threshold frequency. So it's actually going to be hc on lambda 0, which is what we just calculated. So 6.626 by 10 to the negative 34 by 3 by 10 to the 8 on 6.06 by 10 to the negative 7. Okay. .28 by 10 to the negative 19. Just gonna say, let's just say 3.3 by 10 to the negative 19 joules. Probably wrong. Probably messed up somewhere there. If the strength of the magnetic field is 5 microtesla, determine the maximum radius of the photoelectron's path through the magnetic field. When light of wavelength 450 nanometers was shone onto the metallic surface, show you're working. Okay, so I think they're saying, you know, we put it in the magnetic field, it's going to be moving in like a helix shape because it had that initial velocity and now it's curling around. The force, the magnetic force that's pulling the particle in, we can think of that as like the centripetal force, right? So we found out, remember, that using our FBI, that the force was like doing that. So the centripetal force is the it's the magnetic force. So we can calculate that magnetic force, calculate the centripetal force, and then maybe calculate the radius of the circular motion. So let's have a look at that. Zach, yeah, maybe. Depends how it goes. Depends if I make it. Strength of the magnetic field. All right, so let's calculate. We know that this is going to be a QVB sine theta situation, I think. Now, okay, we know that we found out our EK relationship, but all we really need to do is read the graph here. If the strength of the magnetic field is 5 millitesla, and the wavelength of light 450 nanometers. So let's just do 1 over that wavelength. So 1 over 450 by 10 to the negative 9 is that. So 1 on 450, so 1 on lambda equals 2.2 by 10 to the 1, 2, 3, 4, 5, 6, which is on our graph. So we can read off the graph. We're saying at this wavelength, 2.2, right? And the kinetic energy there is 0.7 electron volts. So EK equals 0.7 EV from graph. Now, it might not even be one of these. I think we know, yeah, just scratch what I was saying about QVB, because we can find the velocity without it. So 0.7 by 1.6 by 10 to the negative 19 joules. Which is 1.12 by 10 to the negative 19 joules. Now we know that's 1/2, also 1/2 mv squared, which is, so we're looking for v, so v is going to be 2 times 1.12 times 10 to the negative 19 on mass of an electron. Yes, I am in year 12. Not what I'm looking for. Where's my data book? Okay. We're looking for mass of an electron because we've just divided both sides by m, if that makes sense. Oh, and the square root of this too, because it was v squared. 9.109 by 10 to the negative 31. All right. 2 by, let's pop that in, 2 by, is it 1.16? It's 1.12, not 1.17. 2 by 1.12 by 10 to the negative 19. 109, 10 to the negative 31. So that's going to give us a velocity supposedly of like 5.15 by 10 to the 5. Now thinking circular motion, like we were talking about before, that still applies. So V equals 2 pi r on t. No, we might still need to do a QVB. I can't. Yeah, because where's B going to come into it? So the force, if we knew the centripetal force, we know centripetal force is mv squared on what? On r. So we know m, we know v squared, and we can find the centripetal force, QVB sine theta. I'm going to ignore the sine theta because we haven't been given an angle. So I'm just going to say F equals QVB. And we know the charge on an electron, we know the velocity, and we know the strength of the magnetic field. So charge on an electron is just 1.6 by 10 to the negative 19, ignoring the negative, of course, by 5.15 by 10 to the 5, by 5 microtesla, 5 by 10 to the negative 6. So that's 4.12 by 10 to the negative 19 newtons. Now, okay, so centripetal force is mv squared on r. So that we know r equals mv squared on fc, which is going to be massive electron. Really, we're just going to use, we know mv squared is 2 times that. I shouldn't have crossed that out because we did use v, but whatever. So it's mv squared on, really, man, we could have saved ourselves a lot of time here. So we're saying fc equals mv squared, sorry, r equals mv squared on fc. Now, that is equal to mv squared on QVB. So really, we could have saved ourselves a whole lot of time there. Never mind. Let's just sub in. Stop trying to be smart. mv squared on R on FC, which is going to be 9.109 by 10 to the negative 31 times v squared. Times what? 5.15 by 10 to the 5 squared on 4.12 by 10 to the negative 19. Okay. And that's 0.58 meters. It's an answer. They've given us all that working out space too. 2 asteroids experience a gravitational force of 3.3 by 10 to the 3 newtons between them. Their masses are 2.7 by 10 to the 17 and 6.1 by 10 to the 15 kilograms. Calculate the distance between the 2 asteroids. Show your working. Okay, that should be doable. We know F equals GMM on R. So we're looking for R. R equals GMM on F. We've got the 2 masses. We know big G. We know F. Should be a simple sub. Big G is what? Big G is 6.67. 6.67 by 10 to the minus 11 times the 2 masses, 2.7 by 10 to the 17 times 6.1 times 10 to the 15, 3.3 by 10 to the 3. and supposedly 3.32 sig figs. So 3.3 by 10 to the 19 meters. See about that. Another one of these. Okay. The graph shows the gravitational force experienced by a rocket of mass 750 kilograms as it approaches an asteroid. Determine the mass of the asteroid. Show your working. Well, let's draw our line. And we can do a gradient calc. Rise on run. So it's going to be 25 minus 5 on run, which is 45 minus 10 times 10 to the minus 13. So that is equal to, oh, not even 10. So, no, wait, yeah, we're going to pretend that's a point on the line, aren't we? So 25 minus 5, 45 minus 10, 10 to the minus 13. Not what we were looking at. So, look, my calculator's not having any of that. We'll just say 35. 5.71 by 10 to the 12. What is that? So we just calculated the gradient, which is going to be change in gravitational force on change in 1 on r squared, which is just equal to the product of fr squared. So we've cancelled the change signs, multiplied both sides by r squared. And that's constant. It's the gradient, 5.71 by 10 to the 12. Okay, so how can we use that? Well, let's think about the formula for the gravitational force of the rocket. So the actual sort of equation for what we're dealing with here. Where are we? Gravity in motion. So F equals gmm on r squared. And we're looking for big M. So F equals gmm on r squared. Now we're looking for big M. So let's start by doing our fr squared, right? Equals gmm. And M equals fr squared on g little m, right? We know all that. So we know our constant fr squared is going to be the gradient, 5.71 by 10 to the 12. And gm, so little mass is the mass of the rocket, and big G, of course, is the gravitational constant, which is, I just used it, 6.67 by 10 to the minus 11 times 750. Yeah, that's SI unit, that's fine. So 5.71 by 10 to the 12, 6.67 by 10 to the minus 11 by 750. So we get a mass of the asteroid 1.14 by 10 to the 20, which to two significant figures, that is 1.1 by 10 to the 20 kilograms. Okay, a person spins an object 4.3 meters above the ground in a horizontal circular path of radius 0.8 meters. They release the object horizontally, allowing it to travel to the ground. Calculate the centripetal acceleration of the object before it is released, given it takes 5 seconds for the object to complete 12 revolutions. So you're working. Okay, first we'll calculate the period. So if it does 12, remember, period is time for 1 revolution. 12 revs in 5 seconds is going to be 12 divided by 5. 2.4, sorry, no. So time for 1 rev, 5 seconds over 12 revs is going to give us 0.42 seconds per rev. seconds per rev. So that's 0.24 seconds. That's the period, seconds per rev. Now, we may not even need to know the centripetal acceleration of the object. I just calculated that because I wanted to, did I? Well, we can use that to calculate the velocity, which we do need. So velocity is 2 pi r on t, which is going to be 2 pi times 0.8 meters on 0.42, average velocity. And that's going to give us, what, 11.97 meters per second. Okay. So 4.3 meters above the ground, horizontal circular path of radius. Now, we do know that the centripetal force here is actually coming from the gravity, so I should have just drawn a diagram. If they're holding this thing and they're spinning it, like that, they release the object horizontally. Wait, what? They spin a spin an object 4.3 meters above the ground in a horizontal circular path. Yeah, okay. So that's 4.3 meters. And the radius is 0.8. So if they release the object horizontally, they're cutting that rope, right? But the whole centripetal acceleration thing does still stand. Oh, okay. We don't need centripetal force. We just need centripetal acceleration, which is v squared on r. So we just calculated v, 11.97 squared on 0.8. Which is 179.1 meters per second to 2 sig figs, that's 180. So 180 meters per second squared. Calculate the total horizontal displacement for the object after it's released. Okay, now we're talking about really just projectile motion. So we've cut that rope. We know the acceleration of the object at the time that it was released was, who got 5.48? Someone, never mind then. Oh. How'd you get 5.48? What did you do? I'll continue though. The idea is, okay, so it's just projectile motion really, because we have something, we know its initial velocity, we just calculated that, we know its acceleration, and it's a projectile now, it's free, the only force acting on it is gravity. So we're going to start with vertical displacement to know when it hits the ground, so time of flight, yeah. And then we're going to go and use that time of flight to calculate horizontal displacement. So using that, our projectile motion formula, Sy equals 1/2 gt squared plus uyt, right? We're saying 0. It's 4.3 meters above the ground. So, if it is 4.3 meters above the ground. Yeah, we want 0, sorry, and it starts at 4.3. So it's going to be 1/2 times, minus 4.3. So sorry, remember displacement change in position. If we're starting 4.3 above the ground, our initial displacement is 4.3. Our final displacement is 0. Of course, it's going to be change in displacement is negative 4.3. So 1/2 times negative 9.8 times t squared equals, and then initial velocity in y direction. So 11.97 is the velocity in the x direction. No. Yeah. So remember this loop is horizontal. So if we're moving in a horizontal circle, and this is our horizontal plane, then we have a horizontal initial velocity, but we don't have any vertical velocity initially, so it's going to be, there's just no uy t term. It's going to be plus 0t. So we get negative 4.3 is negative 4.9 t squared. T is square root of 4.3 on 4.9, which is 0.94 seconds. Okay, now the horizontal displacement, we know that's uxt. We do have an initial horizontal velocity. Yeah, we have an initial horizontal velocity. Yeah, we calculated, I was talking about the centripetal acceleration before, but we haven't actually used that because we've cut the rope. So we've cut the rope that was exerting the force, the centripetal force. There is no centripetal acceleration, we're just talking about gravity. So ux is that velocity that it had, so 11.97 times t, which is 0.94. 11.25 meters. That's my suggestion, 2 sig figs, so 11.2 meters. That is the end of the paper though. Let's mark it. I'll just turn on some lights. All right, let's mark this puppy. Marking guide, what do I do with it? Okay. I don't think I got this one. I was really struggling with this one. Not vague, I just don't really understand the idea of simultaneity. They've said in their marking guide, okay, so the 2 marks are for explain simultaneity from the perspective of astronaut A and 1 mark for B. Now I think I've got B down pat kind of. For astronaut A to observe simultaneity, light from the first spaceport will need to travel further than light from the second spaceport. Now, I will admit I just don't really understand this one because astronaut A moves from one spaceport to the other at relativistic speed and observes the lights on both spaceports turn off at the same time. So they're like, is it even about velocity? Is it about speed? You know, they're saying astronaut A is moving. So they've moved from one spaceport to the other at relativistic speed. Does that mean astronaut A is, so this is spaceport 1 and that's spaceport 2. Does that mean astronaut A is standing there? So I can understand that, right? If A is right here and B is equidistant from both of them, then the light needs to travel the same distance to get to B. Light from 1 and light from 2 needs to travel same distance. Except for A, the light from 2 needs to travel hardly any distance. Light from A needs to travel the distance between them. So I guess you could say, oh, if this one turned off, light from the first spaceport will need to travel further than light from the second spaceport. You could also say, I guess, let's say it's about velocity. Astronaut A is moving towards this light source and moving away from this light source. So they're moving towards this light as it comes to them and moving away from that light, like the flashlight on a train. Yeah, I want to read my notes again for that one because I'm not really sure I understand it. We're doing that. The flashlight on the train is what I have written about here. a light positioned in the center of a train carriage. So if you're moving with the train and there's lights on either side, sensors for light on the other side. So let's say we had a train and there's someone in the middle moving with the train and there's two flashlights, maybe. Let's think about that. And they're moving with the train, they're equidistant from the flashlight, so the light reaches them at the same time. Now, the observer will see the person moving this way to meet the light. It is this. I'm going to have to look at that one later. I just can't quite wrap my head around it right now. I think, look, they want you to start with astronaut A. They want you to start by saying, yeah, okay. So ignoring this, I think I've got one mark because I've said there is a loss of simultaneity. So I've got 1 out of 2 there. But the ideal response would have been, we have simultaneity in one frame. So I need to explain that with the idea that the light from the first spaceport, even using this idea, that they've traveled from one to the other at relativistic speed, the light is going to have to travel no distance, I suppose. So we say the light from spaceport 1 needs to travel further than the light from spaceport 2 to reach astronaut A. So for astronaut A, the light needs to, the light from the first spaceport needs to travel further than the light from the second spaceport to be observed simultaneously. However, for astronaut B, the light needs to travel the same distance. So the light from the first and second, the light from the first and second spaceports travels the same distance. Hence, simultaneity. Cannot be observed. Something like that. if astronaut A observes them to be simultaneous, well, we could add another sentence in at the end there. So if astronaut A observes the lights switching off spontaneously, then astronaut B cannot possibly measure them switching off spontaneously because the lights are traveling different distances, if that makes sense. If astronaut A observes the light switching off spontaneously, astronaut B cannot, not spontaneously, simultaneously, cannot also observe simultaneity. Something like that. That would get you the second mark. What have they said for number 2? Up quarks are fundamental particles which experience the strong nuclear force. So identifies the difference between the nature of particles. I think that's baryons versus leptons. Yeah, we got that one. And the other one, they're saying interaction of forces. Now, I've said quarks are subject to the strong nuclear force, but tau particles are not. Unlike quarks, they do not combine with other leptons to form subatomic particles. Yeah, I could have also said, but are subject to the weak nuclear force, but I've contrasted the forces, so I think I will give myself that mark. Now, recognizes the scenario relates to electric field strength and electron change. Yes, I mean, they're just kind of talking about the gradient there. Now, I've shown that the gradient is equal to 1 on Q. I have determined the gradient on this page. It's a bit different to their gradient, that's okay. And I have determined the average charge. And I guess mathematical reasoning is just the steps in between. 4 marks. From the graph, oh dear, so they've said 33 newtons. I guess it depends how you read it. At a distance of 5, at an electric field strength of 2, 2, 4, yeah. Look, the way I've drawn my line, my FG is definitely 34. But their calculation is completely different. So they've gone ahead then and said they haven't even done a net force thing. They've gone, the gravitational force is moving the, yeah, interesting. So I can't quite figure out why they've done what they've done. I've gone ahead and said, okay, the net force is going to be the vector sum of the weight force and the electric force. And then work is force times distance. Now, if it's suspended between the plates, we've said it's suspended, so I guess they're pointing out that at the point before it's moved 5 millimeters at the 0 displacement, it starts from the same kind of position as the other oil drop, in that the magnitude of the electric force is equal to the magnitude of the weight force. So the work done is going to be no. Yeah, I just don't understand that one. Move the oil drop a distance of 5 millimeters towards. Well, okay, let's read the answer then. Work done, yeah. Change in electric potential energy is going to be equal to work, which is, force times displacement, force Fs, whatever. Any extra force would have to counteract the weight force, says Kyle. It's interesting that they've just gone ahead and used the weight force. I think they're making the argument, right, that say work done in an electric field, we can use that W equals QED. This isn't what they've written, but I'm assuming this is kind of what they mean. And E is F1Q, so that's your electric force. So it's just electric force times D. Yeah, E equals and then sub into W equals Fs. I think that makes sense. So you're using the whether it's E equals F1Q or the fact that Fe equals Fw at this point, the electric force equals the work force, and work done in an electric field is electric force times distance, then that's just the weight force, because electric force equals weight force. So that's what they've done. They've gone work equals weight force times distance. Yeah, I guess. I don't know what I've done with the whole net force thing. But I guess that makes sense. So if I was to redo that one, it'd be something like, okay, so we want to determine, we've from graph, we know the weight force at that point is 34 newtons. That's my graph at least. Then the electric force is electric field strength on Q. And we know electric field strength, electric field strength is F on Q. So I guess, and that's the electric force. And we know the electric force is equal to the weight force. So really that's Fw on Q. And then Fw equals EQ, or Fe equals Fw equals EQ. Yeah, all right. And then W equals QED, which is just Fw times D. Yeah, I don't know. Imagine you are pushing on a rock and it isn't moving. You have to add extra force to move it on top of what you are already putting in. It's not a case of net force because the force applied has to be in the one direction to counteract the weight force, I guess. I kind of get what you're saying, Kyle. I think, yeah, you are right there. Like if I say there's a really heavy block on, like a frictionless plane, and I'm pushing, that block, is resisting me pushing it with a force of 50 newtons. I can push it with say 30 newtons, and I'm still doing no work on the block. I can push it with 50 newtons and I'm still doing no work on the block. The block isn't moving. I can push with 70 newtons and the block is moving, But the work I'm doing on it is not 20 times the distance, it's 70 times the distance. So, yeah, I think I get what you're saying, Kyle. I'm not doing 20 newtons of work, I'm doing 70 newtons of work. I'm doing all the work required to overcome the force, plus, what I'm doing in excess of that. Yeah. I'm gonna, don't know what I'll give myself for that. Determines weight of the ore drop. Well, we got that one. We got one mark. Work done in an electric field. We got W. Determines correct substitution. Probably not. Determines work done. Maybe follow through. I'm going to give myself 2 for that. So that would be a 6. 6 out of 8. Inclined plane. 26 kilos. Great. Appropriate mathematical reasoning, sure. The component of force on the object acting down the plane, that's our x component of weight. At the end of the day, the work is being done by the electric field, not some. Yeah, if I was the electric field in that instance. I'm a bit curious as to why. So they say it's been suspended between the plates, and all of a sudden, work is being done to move it. So is it really suspended? Because to remove it from that suspended state, surely something would have to change. I don't know. Yeah, I think I'm sort of following. I don't know. Identifies equivalent forces acting parallel to the plane, sure. Yeah, FA equals FB, we recognize that. Okay. That one was pretty good. Identifies that the interaction involves an electron and a positron. Sure. Photon is exchanged, we got that. Both particles change velocity. I didn't say the velocities changed, but I said they go from moving towards each other. Kyle says, force is always being applied, but work isn't done because W equals Fs depends on displacement as well. I suppose so. Is work being done by the electric field? Yes. Or the gravitational field? The electric field. So we move it with the same force, all of a sudden it's moving. And there's a displacement involved. Yeah. Okay, another oil drop was suspended between the plates with an electric field strength of this. And that means that the weight of the drop was 34 newtons. So to move that oil drop a distance of 5 millimeters towards the negatively charged plate, it has to lose electric potential. If we're moving an electron towards the negatively charged plate, it's losing electric potential energy, sorry. So work is being done by the field on the electron, sorry. Work is being done on the field because the field is gaining electric potential energy, like the electron field system. So it's not an electron, sorry, just a negatively charged thing. I think it's a matter of the gravitational force is moving the oil drop down towards the negatively charged plate. Yeah, yes, Kyle, brain explosion. It's moving it's a negatively charged oil drop. The closer it gets to this negative plate, it does not want to go in that direction in the electric field. If the electric field was just having its way, it would smash into that positive plate. So these areas here are low electric potential energy. These are high electric potential energy. Now, we move this guy towards the negative plate, and the force of gravity is responsible for that. And we're moving at a distance of whatever, 0.005 millimeters. We're moving it against the field so it's we're moving it with the field, but it's negatively charged. So the potential energy of the electric potential energy of the field and the electron, like as a system, not the electron, the oil drop, their electric potential energy goes up because they now have more capacity to do work. They can do more work to hit the positive charge plate. They want to go there more. So we've done work. So gravity maybe has done work on the oil drop, maybe slash the field, to move it 0.005 meters. So by that logic, okay, well, the work done is the force doing the work times the distance it moved. That's the best I can do. Not net, and yeah, I think I'm following you, Kyle, that work done, it's not net force. Because if I was pushing the block with 70 newtons of force and the block was resisting with 50 newtons, I'd still be doing 70 newtons times distance of work. I'm still working that hard. On this one, yeah, I didn't say they changed velocities. I said initially they're moving towards each other and then subsequently they're moving away from each other. I'm not going to be nice though, so I would need to say subsequently the particles change velocity. I'll just include that word. And move away from each other in space. We'll get 2 out of 3 for that one. Okay. They said curve to the right. Yep, cool. The x-intercept corresponds to the threshold frequency for the metal. We did identify that. And I determined threshold. I determined threshold wavelength. Which I'll give myself this. So they say determine threshold frequency. I'll determine threshold wavelength. Recognizes the scenario relates to work function, sure. Provides appropriate reasoning. Determines the work function. Yes, that should be fine. 2 sig figs, 3.3. Sorry. They've gone ahead and said inverse of wavelength to read off the graph, which we did. Determines corresponding inverse of wavelength, 2.2 by 10 to the 6. Determines the maximum kinetic energy of the photoelectron. 1 point. Yeah, we did that in this calc. This one was a mess because I crossed it all out. Velocity of photoelectrons, so I found the velocity. Does that mean 5.15 by 10 to the 5? Sure. Determines the maximum velocity. Force, yes. F equals QVB. Radius of the circular path. F equals mv squared on r equals mv squared on f. Provides appropriate mathematical reasoning to determine radius. That's my timer. Yeah, we had excess time there. Yeah, I'm feeling you on that one. They like to combine topics and stuff. It seems. and there's not much we can do about it. That one went alright. That was 9 marks. Jesus. So 1, 2, 3, 4, 5, 6, 7, 8, and there must have been yeah, there was like a mark for something or other. Mathematical reasoning, maybe. Alright, this one was fairly straightforward, I think. GML 1 R squared, 5, oh, right, they've got something a bit different to me. Oh, I didn't square root it. So GML 1 R squared, root all of that. Or R squared, yeah, you get it. So just put all that in the square root zone. And then that's 5.7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 5.7 by 10 to the 9. Oh, 5.8, rounding up, yeah. Okay, fair enough. Newton's law of universal gravitation. I just I just fixed my answer and now I'm giving myself the marks, but appropriate mathematical reasoning, distance between asteroids. Okay, ignore that. Yeah, so Newton's law of gravitation again, and then appropriate mathematical reasoning, sure, determines the gradient, yes, determines the mass of the asteroid, 1.1 by 10 to the 20, oh, that's 4 marks, not 5. Okay, that's really good. Yay.